Whirlwind tour of neuroscience, meta-learning, debates around likelihood and not likelihood, and Harry started this morning actually saying that the missing thing, Marta is going to come and tell us about the missing ingredient of symbolic representation. And so for the last session we wanted to have that discussion. Marta did this work as a PhD student at Imperial College and has for the last few months joined us at DeepMind and worked with us as a colleague. And Marta is now sort of one of those people who's become known to think about deeply about those problems and tasks, and sort of you can see this in the symbolic representation, so we're really looking forward to that. Thank you.
Okay. Hello everyone, thank you for coming. I'm very, very excited to get the opportunity to talk at DALI. I'm very aware as well that this is the last presentation of the last day, so I tried to make this presentation as full of images and as high level as possible, and maybe we can start a discussion going. So first of all, I am not from a symbolic background myself, but I wanted to give you maybe a high level intuition of what symbolic classic AI is. So symbolic AI is a framework that works with symbolic representations, that's the name, which are language-like propositions that describe formal logic. So they consist of constants and predicates, where constants would be objects or entities in your data set, and the predicates are the relations between those constants. So to give you an example that most of you will be familiar with, if we look at this very famous family tree, the constants would be the people, so we have Abe, Homer, and Lisa, and then we can think of predicates like being a father, so Homer is the father of Lisa, and that would describe the relation. So this way of thinking about data already is quite useful if you are thinking about high-level reasoning in terms of objects and relations, and this is something that we do not necessarily do in machine learning, but helps for this reasoning. So once we have this simple predicates, we can go further and define more complex relations. So once you know, for example, who's everyone else's father in this decision tree, you can go ahead and define what is a grandfather. So if the father of X, if X is the father of Y and Y is the father of Z, then we know that X is the grandfather of Z. And with this definition, you can then query your data set and use any solver to answer you whether Abe is the grandfather of Lisa or Abe is the grandfather of Link, and so on. Of course, applications of symbolic learning, this dates back a while actually, and applications have been many and also successful, so this does not just stay within these very simple examples. They are actually quite successful at something that neural networks are not necessarily this successful, which is being very interpretable, and have thus been applied at things like expert systems. This particular one is a rule-based expert system for medical use, so it would give you advice based on your symptoms. But you can also imagine having some complex planning tasks actually, like trying to navigate this underwater robot through a lake, and this was done also based only on symbolic AI. So some benefits that I think are very interesting to keep in the back of our minds when we do machine learning are the following. The representations are interpretable, and this is something that we've discussed today several times, whether this is a benefit or not, and I guess it also depends on your application. When you're talking about applications like this medical one, it's very clear that we want transparency and interpretability, but it also goes beyond that. If you're trying to build in prior into your models, often it's easier if you know how to deal with these representations, if they're somewhat understandable, and it might be also easier to combine, which also binds to the last the performer talk, to combine different representation and knowledge across tasks if you have a representation that is interpretable, at least for us humans. There is generalization at concept level through reasoning. This one you almost get for free because you're basically reasoning already at concept level. You're basic building blocks are concepts and relations. So the moment you generalize, you're going to generalize at a much higher level than the pixel level generalization that we're usually used to in machine learning. And finally, there's also something to be said about the amount of research that has gone into this field. There are very well-established planners and solvers. There's theory, and there's a lot of knowledge that might not be worth completely throwing overboard with deep learning, and maybe keep in the back of our minds. Of course, the very big downside, and what makes it probably one of the lesser used approaches, is the fact that you have to handcraft all of this knowledge. And this is a very, very big downside, right? Because in the example I just gave you, the information we have is inherently very structured, the objects are clear, the relationships are defined, and it's all really, really easy. But most of us deal with this. So the real world is messy, and it's not only a matter of this is going to be a lot of work to actually handcraft into features. It's not even clear at what level you should start handcrafting, what resolution, what makes an object, what information do you need. This is a task that we cannot tackle. It makes the symbolic methods, in that sense, a bit more inconvenient. A group of models that exactly overcame this necessity of handcrafting are neural networks. And of course, everyone here knows what neural networks are and how they work, but just at a higher level to try to compare them to symbolic methods. Symbolic methods basically put a lot of emphasis on you're going to go into your data and you're going to handcraft some features, and these representations were the center point of these methods. Neural networks, on the other hand, are basically the opposite. They say, okay, you're going to have a task, like classifying pictures of dogs and cats, and which has an input and an output. And all I'm going to assume is I have this black box model that relates these inputs and outputs through some set of nonlinearities, and there is very little there are very little constraints on the representations themselves. There might be constraints in terms of the data type. So when you have images, you're going to have convolutions, but there's no semantic constraints or symbolic constraints, basically. The representations can take any shape. And this is really good, because basically what it does is it turns our problem into an optimization problem. We just have to find whatever weights bring our input towards our output, and that's it. But again, this also has its downsides, and they're very similar to what were the upsides of symbolic learning. We've heard today they're not interpretable. And we've discussed that at length. They're also not generalization at concept level. And this is actually something, I don't know if back in the day when DQN first came out, if any of you ran the experiments yourself on your computer, and if you watched a train, it was quite frustrating, because you would have the little ship, it got hit by a bullet, and you're like, okay, it learned that that was a bad thing, and then 3 episodes later, it shifted by 3 pixels, and it got hit by the same bullet. And this is a very slow, very data inefficient way of learning, right? Because it is learning it is exploring at a state space level which corresponds to the pixel. So it's exploring pixel space. So obviously, it's not doing this higher level generalization, which is of course not trivial, but it's very, very data intensive. And finally, it's not compatible with all these solvers and planners, of course, because these algorithms are so different that they're very hard to combine. Of course, on the other hand, as we mentioned, the knowledge does not have to be handcrafted, and we can learn it from data directly, which is a huge benefit. And there's many other more benefits, not to say that those are the ones, but I think these are some ones worth highlighting. So if you look at the list that I just mentioned for both symbolic and machine and deep learning methods, they're quite complementary, as you can see. I mean, I've narrowed it down a bit. So what motivated our project, and the message maybe of this talk as well, is I'm not saying symbolic methods are the one to go, and it's not realistic, and I agree. But when you're thinking about your models and about the representations that you're going to obtain, maybe it's worth drawing some inspirations of why these symbolic methods work so well and why they enable this reasoning, whereas the current representations we have don't, or at least under a lot of data consumption and so on. So with this idea in mind, we started this project, in my early PhD, this was a couple of years ago, where we wanted to have a simple proof of concept model for exactly this idea. Like, do we benefit from building in these symbolic kind of priors into our model? And what we basically wanted was a system where you would have initially a part that extracts symbols, so to speak, from images, then condensing them into a representation, and then finally carry out learning and how to act in a simple environment. I'll start by describing the environment. The environment was quite a small one. You were an agent, which is the cross in the middle. You can move across space, and whenever you encountered another symbol, you would eat that symbol, and it would either give you a positive or a negative reward. Because we were very interested in generalizing at a higher level as well, at a concept level, we had two versions of this game. One where it was on a grid, so the positions were always the same, the reward is always the same, and one where the positions were random. Keep in mind that the reward, the circle was always positive. The only thing that changed is the starting positions of the objects at the beginning of the episode were mixed. So the first part of our model, we wanted some symbol extraction, but the whole point is that we wanted it to be done with a neural network. We didn't want to sit down and handcraft those features. So we thought, how can we extract information from neural networks? And what we did is we just passed our environment through a convolutional autoencoder, very simple, and took the activations of the intermediate activations and had a look at those, because these contain a lot of information already. We looked at the salient activations, and those gave us position of salient points in the image. So that with that we had the positions of the symbols, and then in order to classify or to give them a certain type, we compared the spectra across all the filters. What we got here is not necessarily 1 point for each object, so a symbol doesn't correspond to an object because we didn't want to handcraft each single object. So sometimes if an object was big, like a cross, it might be 2 points, and when things interacted, they would also give rise to new symbols. So we didn't have a one-to-one translation, but the model downstream would have to learn to deal with this. But what this gave us is we had positions and types of objects. So we already extracted that information from a very simple autoencoder alone. The next step was to do representations out of these. We were very interested in relational representations, especially because the game was also very relationally geared, right? You were always your position in relation to the other objects. And what we did for this, basically, we compared all-to-all of positions of the different object types. This is similar, actually, to the relation nets work that has been done after that. And this gave us the representation that we then used for reinforcement learning, where we basically trained a different Q value for the different interaction types and then picked the highest value. So all of these parts were trained separately. This was a very simple implementation of the concept that we originally had, but you could imagine training this end-to-end and probably better formalized. But the results we got here were the following. When we trained on the grid environment, we had DQN, who very quickly learned to go along the diagonals and get all the points, and it did fantastically. By the way, what we're looking at, I should say, is the percentage of positive points collected. So it gets to randomly move around, and you'd hope that it only gets positive points. Our algorithm wasn't quite as good. The object detection wasn't probably fantastic, so there were a couple of hindrances in the way, but it mostly learned to do well. And we were also not trying to outperform DQN. That was never the intention. But then when we moved on to a random environment, that's when things got interesting. Because our environment, because it was abstracting at a higher level and thinking about relations, it didn't matter for our environment whether it was a grid or it was random. It learned just as fast for both of them, up to 70%. Whereas the DQN took much longer. And after that, we've ran some more experiments, and of course, eventually it learns, but it takes it longer than for our algorithm. And more interesting, another test we did is we trained our algorithm only on the grid, so it's only ever seen these objects in this position, and then tests on random. And this is something where our model did just as fine, whereas the DQN struggled and actually never quite took off. So as I mentioned, this was a very simple initial implementation. So you could improve it on all fronts, basically. We could have a much stronger model at the beginning, maybe even include some of the aspects that we've mentioned today, like beta VAE, and have disentanglement and whatnot. The representation building, again, you could think a bit better of what it is that you want in there. And the reinforcement learning could be replaced for something that is more formally grounded. And we were thinking about statistical relational learning for a while, but there's definitely different options. I also have to point out that the game, of course, was very simple. We're not claiming that this solves AGI. We benefited from the fact that there was basically no background and that it was a very relational and simple game. But we try to prove our point with this, that it helps if you're able to reason at a bit of a higher level. And finally, to finish the talk, I wanted to mention a couple of other papers that dealt with these, what I call the challenges that we have in deep learning that are compared to these symbolic methods, which are, well, as I mentioned, interpretability, the fact that we're not combining them with existing methods, and generalization at concept level. So the one that has been done the most by far, as we all know, is interpretability. There's several ways of doing this. So we've discussed very often today already disentangled. We've heard from Irina about infogan and beta VAEs, and as well as factor VAEs, and we have the poster as well. We heard from Harry about tagger, which also disentangles. And another one that I actually find quite interesting is the structure VAE, where you can assume that your latent variable model has some variables that you know the structure of and some that you don't, and it gives you a framework for combining this information. So can you explicitly feed in the disentanglement, like the digit, and then have the model deal with the other variation. There's other ways of actually looking at interpretability. We can look at more symbolic intermediate representations. So there is work on neural scene derendering, where instead of a normal decoder, what you use is a scene a renderer, and basically this forces you to have a representation that is symbolic enough to feed into a rendering engine. Finally, it's also worth thinking, this relates a bit to our work, what the structure is that you actually want to look at. So if you want to look at relational data and have some sort of relational structure, it might be worth explicitly encoding this in your latent space. And this is what they did for relational nets, where they take their latent space and do all-to-all comparisons between their features. In terms of combining with well-established algorithms, there's not a lot that has been done yet. What people tend to do is they try to tackle experiments that were done back in the day with symbolic AI. So there's program synthesis that you can try to do with neural networks now, as well as trying to understand, for example, if deep learning algorithms can actually learn entailment. So those are tasks from the past that people are trying to see and explore if deep learning can do it. But in terms of combinations, to the extent of my knowledge, there's not super much. And then finally, concept level generalization is another one that hasn't been super explored. Usually work in generalization in deep learning refers to regularization and how can we measure the complexity of our model at a very low level. Although we have, of course, there's also higher level generalization like Irina presented today with SCAN. You could also argue that some of the meta-learning algorithms, to a certain degree, generalize at a higher level than just pixel level, for example. Another thing that I wanted to just maybe comment really quickly is that often the question of generalization is not only that of the model, but also the data you train with, right? So if you're expecting something to train, but it only sees fixed combinations, or it's stuck in 2D space and you're trying to make it understand what a consistent, persistent object is, it might not be able to do that. So it's worth thinking not only about the structure of the models that we make, but also the data we use to train our models. So to sum up, I think, deep learning are very powerful methods. They do struggle when it comes to higher level reasoning tasks, which is what we might ultimately need if we want to get to AGI or to do more complex tasks than the ones we're actually currently carrying out. And when you train your deep learning algorithm, maybe it might be worth thinking about what structures you want to build in, how you want to influence your representations, and maybe take some inspiration from symbolic methods where these particular reasoning tasks actually work quite well. So yeah, that's it. Thanks.
Comments for Marta?
Wonderful talk. Thank you, Marta. I missed the explanation about the reinforcement learning. Was model free or model-based reinforcement?
This one was model free, it was just Q-learning.
Okay.
Yeah.
Second question. Have you been considering model-based?
We did not for this one, but it would make sense, yes.
Another.
So one of the distinctions between neural net methods and the symbolic ones was that in the symbolic case you have handcrafted setup. Do you think it's possible to learn these somehow? Like it's not differentiable, but maybe you can use some sort of evolutionary algorithm or something like that, or is it like a fundamental limitation that cannot be discovered from the data?
I think you can. I think there's something to be said about wanting to learn representations that are exactly understandable by humans and like look exactly like the symbolic, which might not make sense in the longer term. But I think you would hope so, right? Like we've learned those representations, so there should be hopefully a way of extracting those representations as well from data sets, assuming both your models and your data are rich enough for it to enable to learn that.
So follow up with on your last comment. Do we know that the representations that humans have in this argument you're making are sort of the image object style representations that the symbolic models are using? Was that the argument you were making just now?
Not the argument now, but as to that, there are papers, which I cannot cite from the top of my head, that argue in favor. There's basically on both sides arguing in favor and against it. It seems natural, I guess, to people when they start thinking about these things, but like you said, and someone else mentioned today as well, if we want to solve science, maybe it's not worth thinking like humans think because we haven't solved those problems ourselves, right? So maybe this is just an intermediate step to understand, to obtain certain properties that we have from the symbolic method. So this generalization, this able to learn, this ability to learn fast, and so on and so forth. But it doesn't mean that they will achieve the same intelligence that we do, or that this is the end-all be-all solution. It might just be some way of overcoming certain problems that I think we've learned in my time.
Any other last comment?
It's related to the question that was just asked. So, is there some evidence that symbolic reasoning happens in the human brain deep down when we do solve some tasks, or is maybe the symbolic aspect only an artifact of us trying to communicate certain things through a very constrained bandwidth channel? And it just happens that words and symbolics communication is a very efficient way and a robust way to communicate, but 99% of the reasoning happens in a distributed representation, like a single RNN vector or something. Where is the line, right? And what's your thought on what evidence is there, and where do you feel like maybe in your current research things could fall on that spectrum?
So I'd like to forward to the neuroscience. So I'm not a neuroscientist on this, so it's hard for me to say exactly whether the brain does this or not. I certainly think that this is the way we at least explain problems, because when we sit down and write the instructions, this is how we would set about, because maybe it is the optimal way of encoding the information. So maybe this is also a way, I understand what you're saying. I'm not sure if humans do it that way, but at least we're able to express whatever we want to do succinctly in the symbolic representations. So you'd hope that if a machine at least learns to think in that way, who says that doing it like humans is the optimal way, right? But at least we know that they would have the same capabilities that we can achieve with these symbols. Whether or not that is something good, I wouldn't say.
We have the neuroscientist here.
Yes.
I can try to answer that. So think first, I don't, humans don't necessarily think in terms of the formal symbolic logic that Marta might be referring to, but human mental capability definitely expanded a lot once we invented symbolic language. And it's basically, I think, quite a good that we can't come up with the same, I guess, same kind of reasoning and logic, etc. if we didn't have the internal mode of speech. So I think that there's something to that.
But yes, I'm attempted to bring you into this thought, unless we can move on, and we'll bring you back also. That's that answer.